Hello folks, Mr. Eck here. Today we're going to talk about rational functions. So this is section 2.6. First we should say, what is a rational function? It is a function of the form p of x over q of x, where p and q are polynomial functions. These functions can get pretty exciting, pretty wild. So we're going to start with the basics, the most simple rational function. The simplest possible rational function is y equals 1 over x. So in this case, the p of x is just the polynomial 1, and the q of x is just the polynomial x. But altogether, this gives us a really good insight into the general behavior of how rational functions behave and why they're different than other functions that we've seen before. So with a rational function, we generally want to explore values near infinity to the left and right. That's called the end behavior, as well as values near any undefined places. So the first thing I see with f of x equals 1 over x is that 1 over 0 in my in-out table is undefined. And so we might want to understand what's going on to the left and the right of an undefined value, and what is going to happen in that graph. So let's just go ahead and fill in the entire in-out table. You can do this on your own. I'm going to stop talking and speed up the video while we fill this out. So just a little subtlety is because we're doing 1 divided by x, when we do 1 divided by 1/10, you actually get 10. Or in this case, the one I just circled, negative 10. So as we get closer to 0, we're sort of taking fractions but dividing by fractions. We actually get larger and larger numbers. But let's explore that a little bit later. So the first question is, before we even attempt to make the graph, what happens to f of x as x becomes either very large or very small? So that's talking about the left and right ends of the graph, kind of at around x equals negative 100 or 100. And you can imagine bigger values there. It seems that f of x gets closer and closer to 0. If we were to plot that on the graph, so let's plot a couple of these points, we would notice, that would be negative. We would notice that as we moved out on the graph would be getting closer and closer to 0, but never actually quite touching it. And it would also happen on the positive side. That'd be 1/2, 1/3, 1/4. So the graph would be getting closer and closer to 0, but never quite touching it. So this feature of getting closer and closer but never quite touching is called a horizontal asymptote. Asymptote is maybe a word you've heard before. The Greek definition is not falling together, but it just means kind of getting closer and closer to. You can't actually touch the asymptote. That's a weird misconception. But you're getting closer and closer into it to 0 as time goes on. And using our good limit notation, or not quite limit notation, but sort of arrow faux limit notation, we can write the following. As x approaches infinity, so that's the right end of the graph, f of x approaches 0. This is different than other polynomial graphs we've done before, where you were always approaching either infinity or negative infinity. Now you are approaching 0. And we could also write on the other end of the graph, as x approaches negative infinity, so as you go from the middle out, f of x also approaches 0. Often we represent this on the graph with a dotted horizontal line. I'm going to use red for that dotted horizontal line. Just as a line that the graph should approach, but not cross. It's going to get closer and closer to it as x grows bigger or smaller. So that's what we would consider the end behavior of this graph. Let's now talk about the behavior in the middle of the graph. That is kind of right between here. So when x was equal to 1/10, y was equal to 10. Or maybe when x is equal to 1/2, y will equal 2. 1/10, y will equal 10. We're close to 0, y will equal 100. So the graph is actually going to shoot up as you get closer and closer to 0 from the right-hand side. And on the other side, it's going to have the same behavior but negative. So 1 over negative 1/2 is negative 2. 1 over negative 1/10 is negative 10, which would be way down here. So this graph is going to shoot further and further to the negative. And this is the complete graph. And notice that it's still undefined at 0. So the graph shoots up to one direction and down to the other direction. This feature of the graph is called a vertical asymptote. I'm not going to put that in quotes. It's a vertical asymptote. And we usually represent that on the graph with another sort of dotted line, which can be hard to see on the axis. And we notice on this graph that the asymptotes intersect at 0, 0, which is not really the vertex. That's not a point on the graph, but it is a convenient location on the graph to sort of study. Before we get into the notation, some other key points on this graph, now that it's complete, that you should always include when you're graphing 1 over x are 1, 1, as 1 over 1 is 1, and negative 1, negative 1. 1 over negative 1 is negative 1. So those 2 points in 0, 0, along with this kind of generalized curve, which is actually in 2 branches but represents one single graph, that's the best graph of 1 over x. I'll clear that highlighter off. So how do we use this notation to write about this vertical asymptote? We've never actually done this before. We've only used this arrow notation to talk about x going to infinity. But since we can't actually write, like f of 0 is undefined. So we're going to use the same notation to talk about what happens at 0. So I'm going to say as x approaches 0 plus. Now that's weird, right? I've never heard of a 0 with a plus exponent. So what does that mean? Well, that plus means from the right side. That is the positive side of the graph. So the positive side of the graph is over on the right. And as x approaches 0 from the positive side of the graph, you can imagine you're sort of shading along the graph. The question is, where does y go? And I can see that I'm shading up off the screen towards positive infinity. So as x approaches 0 from the right side, with which we use that little plus sign, I would write that f of x approaches positive infinity. Let's say positive infinity. On the other hand, as x approaches 0 with a little negative up there, again, not an exponent, but that negative means from the left. Where does y go? Well, in this case, I start to the left of 0, and I highlight 0 from the left. I go down. Oh, look, it's going down. I'm sort of going off the page, all the way down here, all the way off the page. So we would say, as x approaches 0 from the left, f of x is approaching negative infinity. That's the type of notation we're going to use when we have these asymptotes. And that reason we need this sort of like plus and minus is that if we come in from the left, we go one direction, and if we come in from the right, we're going the other direction. So we need a way to denote which direction we're coming from. So to recap the graph of 1 over x, if you had to graph this without plotting points, like I would expect you to be able to do that, not plotting points, here are the features you need. F of x equals 1 over x. You should first draw the 2 asymptotes. So the horizontal asymptote, which is at y equals 0, and the vertical asymptote, which is at x equals 0. Those intersect at 0, 0. You should plot the point 1, 1 and the point -1, -1. And then you're going to draw the sort of two branches of this graph, like that, and like this. And those are part of the same graph. So this is a disconnected, discontinuous graph. And this is a good graph of 1 over x, or an acceptable graph of 1 over x. So those are the key features. 2 asymptotes, and 2 points, and 2 branches together. That makes that graph. Another important parent graph is the graph of y equals 1 over x squared. And we can approach this again with an in-out table. So 1 over 1 squared is 1. That's the easiest value. 1 over 0 squared is still undefined. And as we start to get larger values, 1 over 10 squared is going to be 1 over 100. But 1 over 1 over 10 squared is going to be actually just 100. And the 100s and 1000s are either going to be very small or very big. And I don't think I have room to fit those numbers. On the other side, on the negative side, 1 over -1 squared is not going to be negative this time. It's actually going to be positive 1 still, because we're doing 1 over -1, but it's being squared. So that stays positive. And same with the -10. So that's going to be 1 over positive 100. And -1/10, that's going to be actually just 100. So this graph has apparently some symmetry, because the left side and the right side seem to share the same y values. Similarly, this is going to be very small, 1 over -100 to the second power, and this is going to be very big. We can notice that the horizontal and vertical asymptotes are actually the same as 1 over x. So let's go ahead and just sketch the graph of y equals 1 over x squared. So a horizontal asymptote should still be at y equals 0. And the vertical asymptote should still be at x equals 0. You can see that from the in-out table and the different behavior that you're going to get. We still go through the points 1, 1. But this time we also go through -1, 1, 1, 1, and -1, 1. And this graph, if anything, grows faster. So it's going to be even steeper than 1 over x, although that's kind of hard to draw in the picture. And it's going to get closer to 0 even faster than 1 over x. It's also going to be exactly mirrored on the left-hand side. That got a little too close to 0. That's a little better. It's going to be exactly mirrored on the right side and the left side. Why is the left side now in quadrant 2? Well, because you are now doing 1 over x squared, and the squared makes negatives into positives. So both sides will be above the axis. This does change the notation that we would use for this asymptote. So I would write, in this case, as x approaches 0 from the right side, f of x approaches infinity, and as x approaches 0 from the left side, that's this side, f of x is also now approaching infinity. So I would change the notation if I was describing that asymptote. But this is the graph of 1 over x squared. It's slightly less useful than the graph of 1 over x, but it's a really good parent to know. So the two graphs, 1 over x and 1 over x squared, you should know what they look like, and you should be able to plot them without plotting points. You should just be kind of at a point where you see those graphs and you know what they're going to be. Flipping to the next side, one key idea is that the standard transformations that we learned way back in chapter 1 actually apply to 1 over x and 1 over x squared, just like they apply to everything else. So for example, if I have 1 over x plus 3, you could think about this as 1 over x shifted left 3 units. And we remember what the graph of 1 over x looked like. So let's see if we can construct this graph. Well, 1 over x had asymptotes that crossed at 0, 0. It had a point at 1, 1, and -1, -1. If we're shifting left 3 units, you're going to take all 3 of those points, including that middle point where the asymptotes cross, and move all of those over 3 units. So that's going to go over 1, 1, 2, 3. The asymptotes are now going to cross at -3, 0. So I'll draw new horizontal and vertical asymptotes right here. Then I'll plot the points that the graph contains and sketch the rest of the curve like this. Notice how I did that without actually plugging in any x values. Plugging in x values is not going to really help you here. You've got to know what the shape looks like. We can check that is x equals -3 undefined? Yeah, it is, because -3 would cause you to have 1 over 0. So that has to be where the asymptote is. You can also check that these other values work, but I already know they work, so I'm not going to check. But you could test that. So that's how you graph a transformation of a rational function. Let's graph another transformation of 1 over x squared. So there's two transformations happening here. There's a negative and a +2. We know from chapter 1 that you have to do the negative first. These are y transformations because they're happening outside of the fraction bar. So you're going to do the negative first. That's going to reflect over the x-axis. And then we're going to go up 2 units. So first we can think about the parent of 1 over x squared, which would have asymptotes at the zeros and go through 1, 1 like this. So 1 over x squared would look like that. This time I'm going to kind of draw it out with dotted lines. Maybe not the whole thing, but a little bit. Then we reflect that over x. So that will reflect over x. It will keep the asymptotes, but it's now opening down. Like so. And then we're going to take everything and shift up 2 units. So let me actually erase this kind of red graph from here. I'm just going to take the pink graph and shift it up 2 units. So when you shift a rational function graph up 2 units, you also need to shift the horizontal asymptote from 0 up to 2. So that asymptote shifts up to 2. The vertical asymptote has not shifted. That's still at 0. And all the points in the graph shift up 2 units as well. This should look something like this. Something like that. I would say that 1 over x squared should have even symmetry. I notice my graph doesn't look entirely symmetric. This isn't an art class. As long as you have sort of the rough points and I can see your idea, it's okay if the graph's not perfectly symmetric. But you should try to make it as symmetric as you possibly can with the tools available to you. Not all rational functions will look like transformations of 1 over x or 1 over x squared. They can get pretty complicated. One thing that can complicate a rational function is if you have a term that cancels out. And if you do have a term that cancels out, it's going to create what is called a hole, or sometimes called a point discontinuity in the function. So those don't create asymptotes, they actually just create little missing pieces in the graph. Here's an example. Say we have y equals x minus 1 over x minus 1 times x minus 2. In the original function, I can look and notice the excluded values, which are values that are excluded from the domain because they would cause us to divide by 0. And the excluded values here are x equals 1, I should write excluded values, colon, x equals 1, and x equals 2, because x equals 1 would cause us to divide by 0 here, and x equals 2 would cause you to divide by 0 there. However, notice also that you can reduce that x equals 1 term with this x equals 1 term with 1, each of those turns into 1, and this becomes this equivalent expression, y equals 1 over x minus 2. However, even though you simplified it, the simplified version keeps the excluded values from the original version. So when we're graphing it, we're going to graph this, but we're going to use these excluded values. And the x minus 2 is going to cause us to have one of those vertical asymptotes. We can see that this is a transformation of 1 over x. But what about the x equals 1? What does that do? Well, it makes a hole in the graph. And generally, not for this function specifically, but just generally, a hole in a rational function is a part of the rational function where it's going on, doing its thing, and then there's just a missing value, and the function continues on. And a function can have many holes. It could have a hole there, it could have a hole there, it could have another hole over here. It could have as many holes as you want to have factors that cancel, but every time you have a factor that cancels, it creates a little hole, which you represent on the curve of the graph with an open circle. Notice, this is the myth, that the myth is people seem to think that a hole has to be on the x-axis, which in fact it most often is not. A hole usually has an x and y value, that is, it's part of the continuity, the curve of the graph. It's just skipping over one single little value. So how do you find the y-coordinate of a hole in a graph like this? Well, you plug in the value. So you plug in the excluded value that canceled out. So in this case, x equals 1 into the reduced equation. So I have the equation y equals 1 over x minus 2. I'm going to plug in x equals 1 into that. So I'll plug in, if x equals 1, I have y equals 1 over 1 minus 2, which is 1 over negative 1 or negative 1. So that means that there is a hole at x equals 1, y equals negative 1. And we can actually go ahead and just put that right on the graph. The hole will be at x equals 1, y equals negative 1. And you can draw a big open circle right there on the graph. Now, let's actually just make the graph. For making the rest of the graph, you look at the reduced version. So we have y equals 1 over x minus 2. That's like 1 over x, but shifted to the right 2 units. So 1 over x has asymptotes at 0, 0. That's going to be shifted over, so it's going to have a vertical asymptote here and a horizontal asymptote. It's not shifted up, so the horizontal asymptote is still at 0. It's going to go through the point, what would be the point 1, 1 is now the point 3, 1. And what would be the point negative 1, negative 1 is now the point 1, negative 1, but we've already determined there's a hole here, so I don't need to plot that point. I'm going to leave that open circle, but I know the rest of the pattern of the graph. So on the positive branch, it kind of does this, and the negative branch does what the negative branch should do, but instead of having a point there, it has an open circle hole. And that's how you plot a hole in a rational function. You look for any terms that cancel out. Any excluded values that cancel out give you a hole. But you can't just be like, yay, there's a hole there. You have to plug in that value into the reduced version to find the x and y coordinates of that hole. We also can use that sort of fancy arrow notation to talk about the hole. We can't write that, f of 1 equals anything because f of 1 is undefined. There's a hole there, right? That was the whole point of the hole. Whole point of the hole, however, what we can say is that as x approaches 1, f of x approaches or gets closer and closer to whatever the y value of the hole is. So in this case, the y value was negative 1. So we can say as x approaches 1, f of x approaches negative 1. And that's how we could use fancy notation to talk about the location of the holes in the graph. And then one last piece of practice to close the video out. What are the coordinates of any holes of the graph x minus 3, x plus 1 over x plus 5, x plus 1? Pause and think about that for a second. And now that you've paused, let's work it out. So if you write this out, you notice that it has the excluded values. X cannot equal -5, and x cannot equal -1. But this term cancels out, and so this excluded value is going to make a whole. And when you cancel those out, this reduces to x plus 3 over x plus 5. So to find the y-coordinate of the whole, I plug in -1 into the reduced version here. So -1 plus 3 over -1 plus 5. So that's 2 over 4, or 1/2. So for this function, I would say that there is a whole at x equals -1, y equals 1/2, and if I was continuing to make the graph, I would plot an open circle at those coordinates as a point that the graph should connect to. All right, everyone, we've been talking for long enough. That concludes our work for today. Please tune into the next video where we'll talk more about graphing rational functions that aren't just transformations of 1 over x, that maybe have all sorts of other behavior going on. So stay tuned for the next video for that one.